Hello everyone, and welcome to the lecture discussing the coin change problem and its solution. As always, there's a complete solution notebook here describing the solution to the notebook problem. This problem is actually common enough that it has its own Wikipedia entry, and it's a really famous problem in showing some of the issues with recursion in general and why dynamic programming and memoization is such a key tool to improving on basic recursion. So what we're going to do is go through basically two implementations of a solution. One is just a classic recursion that doesn't use memoization, so note the solution is not optimized, and then we go through a better solution. I would really encourage you to read through this entire solution notebook first, as well as read through, if you scroll all the way down to the notebook, there's an extra resource here, Dynamic Coin Change Problem. I would really recommend that you read that entire extra resource. It's just a page long that describes this exact same problem and why there are issues with normal recursion. And also there's the Wikipedia entry that's linked here that you can also read. And there's solutions as far as implementations with dynamic programming, and it's in Python, so you can read about it as well. All right, so let's go ahead and discuss the coin change problem then. We're going to go ahead and jump to some live code here and start by thinking about what the problem statement's actually saying. So we're given a target amount n. So some target amount of money we want to make or change we want to make. 56 cents, 50 cents, 45 cents, 46 cents, etc. And then we're giving a list or an array of distinct coin values. And we want to know what the fewest coins needed to make that change amount is. So for instance, if we jump back to the solution notebook, we can see here that if you have n equals 10, so your target number is 10, and you're giving values of 1, 5, and 10, there's 4 possible ways to make change. You can have 10 ones, a 5 and 5 ones, 2 5s and a 10. And the correct answer for the minimum amount is, of course, just one coin, that 10-cent coin. So what we're going to do is first do a classic recursion solution to this problem. And then we'll talk about what the issues are with that solution. So let's go ahead and get started. First, I'll start just by calling def rec_coin. I'm going to take in, I'll call it the target, and then the list of coins. So what I'm going to do first is think about certain base cases or certain scenarios where I should instantly return something. So one of those cases is if the target number is in coins. So for instance, in that last example, 10, the target was actually in the list of coin values, you would just immediately want to return it. So we want to see if we have a single coin match. And in this case, we'll just return 1. So the minimum number of coins is 1. If that's not the case, what I'm going to do is set a default value here that the minimum number of coins is the target number. And what I'm going to do is actually recursively solve for that. And at the end of everything, I will return min_coins. All right. So let's go get started at what we actually want to do here. So in plain English, what I want to do is for every coin value in that coins list that is less than or equal to the target number, what I want to do is recursively call my function and add a count coin and then subtract from the target. And then I'll reset the minimum if I have a new minimum number of coins. So that's a little complicated, so let's go ahead and write it out. So I want to say for, let me go ahead and zoom in here so it's really clear. For every coin value that is less than or equal to my target value. So I want to say for I in, and then I'll make a list using list comprehension that's saying C for C in coins if C is less than or equal to that target. So here I'm saying I'm making a list comprehension that's grabbing all the coins for C, if C is less than that target number. And I'm saying for each of those basically coin values, I'm going to make a new variable called number of coins we need. And I'm going to recursively call 1 plus the recursive function here. I'm going to subtract the current coin I'm on and then pass in their coin values, which hasn't changed. And if the number of coins, it suddenly finds itself being less than the minimum number of coins, which we started off as the target number, I'm going to reset it. I'm going to say the min coins is now equal to the number of coins. So this is the full recursive solution. It's inefficient, but it will work for most cases, for cases that have American style coins. If you have odd coin values or weird prime values, such as like a coin that has value 7 or something like that, and you're looking for a distinct number, you may have an error solving with this recursive solution. And that's part of the problem we'll discuss in a second. But basically what's going on here, just to go over this basic recursive solution, which note is not actually the correct way to solve this problem. We have a default value for the minimum number of coins, and we set it to the target. We have what we can think of a base case, which checks to see if target is in coin values list, right? Otherwise, I'm saying for every coin value that's less than or equal than my target, so for every value in that list, I'm going to add a coin count. That's what this 1 is here. So I've already had to use a coin, and then I add it to the recursive call, where the recursive call is now a new target. I will subtract the value of that coin from it. So for instance, if I'm looking for 15 cents and I just subtracted a dime from it, my new target is now 5 cents. And again, I pass the list of coins, searching for that new minimum. And I will reset the minimum here if the new num coins is less than the min number of coins, which we set first as the target. And that's all there is for this recursion. Now, if we actually run this, you'll notice it takes a very long time to run for certain values. I'm going to do a basic example here. So I'll pass in 15 as my target value, 1, 5, and 10. I'll run it. It outputs 2, so that's correct. It needs 1 dime and then 1 nickel. But if I input something else, maybe something as 63, and I'll also pass in a quarter in value, it'll take much, much longer with this. And you'll notice the problem with this approach is that it's inefficient. It can take many, many recursive calls to finish this problem. So I'm going to go ahead and jump to the solutions notebook. I'm going to kill the cell by interrupting it. So I'm going to say kernel interrupt here. And then I'm going to clear its output, cell current output clear. And go ahead and jump back to the solution notebook to show you an issue here. So for instance, let's pretend that I'm looking to solve for 26 here. So if we look at the figure that's in the solutions notebook, each node here corresponds to a call to that recursive function. The label on the node indicates the amount of change for which we are now computing the number of coins to solve for. Now note how we're recalculating values we've already solved. For instance, 15 here is solved for 3 times. Over here, where my mouse currently is, over here, where my mouse currently is, and over here, where my mouse currently is. So it would be much better if we actually kept track of the function calls we've already made, so we don't have to constantly resolve for things we already know. And that's where the dynamic programming solution comes into play, that memoization that we discussed earlier in this section. And I'm going to zoom out so you can see the, whole equation here, or whole code. And the key to reducing the work time for the function is using this dynamic programming. So the better solution is to remember past results. That way, before computing a new minimum, we can check to see if we already know a result. And you won't have this straight recursion call where you look at results that you've already done in the past but haven't saved in memory. Now, something to keep in mind here is that while this is very efficient in time, it's going to be less efficient in memory since you're storing more results. Usually that's a trade-off you would want to make for a simple problem like this, but you really have to think of what's going on in the general scope of your problem that you're trying to solve and see if this is a good trade-off. Usually it is, especially in this context of an interview question. All right, so now what we're going to do is this function is going to take in 3 inputs. It's going to take in a target, coins, and then we're going to have a cache, known results. And instead of actually putting it outside the function, we're going to develop it inside the function. So let's go ahead and live code this dynamic programming solution so we can really understand why this is the best approach to solving this problem. We're going to go ahead and jump back to the live code. All right. So let's start by naming our function, rec_coin_dy dynam for dynamic. And in this case, we've taken 3 arguments: the target, the coins, and a new parameter, results, or known results. So I'm going to do the exact same thing I did last time. I'll set the default output to the target. So far, the minimum number of coins I need is whatever target number gets passed. And then I'm going to think of my base case. So what does that look like? Well, again, if I know the target is in the coins, then I'm going to say known results of that target, and I'm going to set that equal to 1, and then I'm going to return 1. So what's going on here, it means if I kept doing recursive calls and suddenly I find that the target number is actually in coins, then I'm going to set the known results at the target equal to 1. And then I'm going to continue on to what's the more complicated part, this actual recursive calls. And it's going to be an else if statement or an elif statement. And what I want to do here is I want to return a known result if it happens to be greater than 1. So if I know my known results at that particular target is greater than 0, then I'm just going to return that value. And this is the dynamic programming that's going to save you a lot of time in recursive calls. And hopefully it'll be clear once we go through the final else statement. So again, I'm going to say for every coin value that is less than or equal to the target, so for I in, and I'm using list comprehension again, C for C in coins if C is less than or equal to target, I'm going to make a recursive call. But pay attention here because I'm going to include the known results. So I'm going to say num of coins. It's going to look really similar to the last one. Another recursive call here, rec coin, this case dynam. I pass in my target minus I, that current value that I'm on. The coins, the values we know doesn't change. And then I pass in my currently known results. And then I reset my minimum just like we did in the last one. So if my num of coins is less than my minimum number of coins, I can just say min coins is equal to the current number of coins. And here's where it comes into play. I will also need to reset that known result. I will have to say my known results at target is equal to the minimum number of coins. And then finally, I will return the minimum number of coins here. So let's go ahead and check that out. Let me fix a typo here. This should have been known results. Make sure results is plural on all of these. All right, let's see if this runs. Make sure there's no other typos in it. And we will call it, let's say, an interesting target number, maybe 74. My coin values will be 1, 5, 10, 25. And I'm going to initiate my known results just like we did in that last memoization problem by a list of zeros of length target plus 1. And now, if I call my function on my target with my coins and my known results, you'll notice I get 8. Now, if I try doing that on that first function with just target and coins, you'll note it's just taking forever to run because it's making a ton of recursive calls here. So I'll have to stop that cell from running. Okay, so if you notice, the notebook did have a test your solution, but note it was designed for non-dynamic functions, and they will take a long time to test. So if you believed you had a solution, you should have come here and checked this. All right, so let's go ahead and briefly go over what we did here. We tried to create a normal recursive solution, but it would have failed because it would have taken so long because it kept making repeated recursive calls for results it actually had already previously calculated before, as we can see from this diagram of trying to figure out 26 here. All right, we came up with a dynamic programming solution that took into account our known results, but also solved a very similar recursive fashion, just like the first solution, except it updated its known results here, here, and here. And that's really the case of memoization dynamic programming. So once you've gone through this video, remember, you should really check out this great resource here, Dynamic Programming Coin Change Problem link at the bottom of the solutions notebook. Read through it. It's a great walkthrough on the coin changing problem. Or you can also read the Wikipedia page entry here that also explains the dynamic programming solution. It does it in a little bit of a different fashion here by creating a matrix, but again, you should walk through it and make sure you understand it, because there's various ways of writing out this particular dynamic programming solution. All right, so your homework is to make sure you read both that Wikipedia entry and, if you scroll down here, this link here to the dynamic coin change problem. It's going to be pretty similar to what we discussed here. It will also have this figure in it, but it's important to read it because it goes through a very slow and steady solution explanation for the case of dynamic programming there. All right, that's it for this section on recursive interview problems. Recursive interview problems, as far as the way they're presented in interview situations, sometimes they won't explicitly tell you to use recursion. But hopefully, after completing this section, you have an idea of in your mind what situations would call for a recursive solution. And if you're ever confused in an interview situation, don't be afraid to ask of something like, hey, would recursion be a good call here if it's on the brink of your mind but you're unsure? Remember to ask a lot of questions, do your thinking out loud when you're in an interview situation. Other than that, as far as this question goes for the coin change problem, make sure you do that homework reading, and I will see you at the next lecture. All right, great job everyone on the interview questions. I will see you in the next section.